Hi there, these are your parts of an experiment notes. Be sure to follow along. You will read and you'll listen and watch and to fill in all your blanks in these notes. Here we go. Scientists will use process skills in order to find answers to questions. You, as a scientist in training, have already learned many of these process skills. So some of these we can go over pretty quickly, and some others we need to take some more time to look at. As you can see on this infographic, you've learned about safety and how to use tools in the lab. You've learned about qualitative and quantitative data, making observations, and following safety. All right, making observations, just to have these all in one place. The first one is using your senses to take in observations would be your qualitative. And I'm going to spell it, but it's also up here in this infographic too. So it's Qualitative. Qualitative. So those are the qualities that you take in with using your five senses to make observations. And the next one, using amounts or measurements in your observations. So this would be collecting data with numbers. So this is your quantitative. Again, it's up here in the infographic for help with spelling, but I'll also spell it for you. Quantitative. Quantitative. So it's a quantity. What scientists make observations about those things around them, they write a well-defined question, and the well-defined question, as you should know at this point, is a clearly stated, testable, write that in, testable question in which includes an independent and a dependent variable. For example, what effect does pH of water have on radish seed growth? So it has an independent variable, which is what you're testing, the effect of pH, or the effect of water. And the dependent is what you're measuring, so it would be the seed growth. So the pH of water is your independent variable, and your seed growth would be your dependent variable. A hypothesis is made next. And a hypothesis, once you've written your well-defined question, you're going to think about what you expect to happen. So write this in. It explains what you expect to happen. What you expect to happen in your experiment when you test your question. It also will include an independent and dependent variable, and it can be written in the if-then statement, so like a cause and effect. For example, if the pH of water is a 7, then the radish seeds will grow 55 centimeters. In order to test, though, you must have procedures. The procedures are all your steps that you have written out. So it'll also be a numbered list, to be specific. It's a numbered list of steps to follow to test your hypothesis. Numbered list of steps to follow to test your hypothesis. All right, measuring is what we worked on previously. It's using the metric system. Scientists must be able to communicate their data to other scientists in all of the world, and that's what they use there. So they will communicate in the system that they're all familiar with. So it's going to be the metric system. Sometimes it's called this SI system, which stands for System International. So it might say put the SI unit. Same thing as metric system. All your measurements, your numbers, measurements must include, write that in, must include a metric unit of measurement. When you put the unit of measurement, scientists know automatically what you've been measuring. If you have a G, they know you've measured mass because it stands for grams. If you put a C, they know that you've measured Celsius for the temperature. So what I included next were those pages if you had issues with downloading the book in the science lab. And I also annotated, I highlighted and annotated a little bit what was important from each page. So I thought I would put them here just in case you do need them for your notes over the different types of measurements that we've been working on, what includes a metric unit of measurement. So it has a little bit of everything. And also here, what I like on this additional information, these are the metric units. Well, let me put this metric base units. How you know it's a metric unit of measurement is that it will end with meters, liters, grams, or Celsius in the name. Now, you know, there's a prefix chart that if you are going to use a small measurement, it's going to be milli in front of it. And if it's a very big measurement, it'll have the prefix kilo in front of it. So a kilogram versus a kilometer, or a kilo or a milligram, sorry. Kilogram, milligram. And this right here just gives you like what these measurements and metric system amount to, like to give us kind of an idea in our heads what it's like. So like a millimeter is about the width of a piece of yarn. A gram feels like a dollar bill in your hand. So it just gives you some ideas about what they feel like. Okay, moving on. In order to test, you must have these parts of your experiment. You must have a control group. Write that in. A control group. This is the part of the experiment that serves as the standard of comparison. It's what your object is normally supposed to be like. Normally. And it's where you get your baseline data. You have to know where you begin before you start changing anything to test. So that is your control group. The normal, nothing happening to it. You didn't change anything. It's what it normally does. The next thing you have are constants. What are you going to keep constant? Okay, so these are the factors that are kept the same. Write that in. They are kept the same. And they're not allowed to change to make sure the data collected is valid and reliable. So valid and reliable means that it's true, that it's justifiable. The constants are not what you are testing. Write in the word not. They are not what you are testing, so you want to keep them all the same. Some examples of what you would keep constant. It does depend on what you're testing, but some things you would want to keep constant are the temperature, the time, the type of object you're using, the amounts that you're using. Those are some of the typical constants I could think of. We'll work on that together, like picking out the constants coming up. Next, you have to have different types of variables. And then we've already talked about this, but just to give you some more practice, you need an independent variable. So write that in, please. Independent variable, that's the one variable you change in your experiment. Just the one thing that you're changing because it's what you are testing. Write that in. It's what you are testing. It's also known as the manipulated variable because that manipulated means like to change. So that is what you are in charge of changing. And the other type of variable is the dependent. So we're going to fill that in. The dependent variable is what you are measuring in your experiment. Also known as the dependent variable. So it is dependent on what you're changing. It's dependent on the independent variable. Oh, whoops. I didn't mean to put dependent. It's also known as the responding. Let me change that. because it's responding to your manipulated variable. Let's write in responding. Responding. Knew that seemed odd. Okay, so also you can write this in on independent is the cause, and the dependent is the effect. And that was on your notes from another time, but just wanted to put it here as well. Okay, so let's do some examples. This particular one is which type of water will improve plant growth? So you have the same type of plant in the same kind of container, same amount of soil and so forth, but you're just wondering which type of water. And we have tap water, we have rainwater, lake water, salt water, bubble water, and then no water. So which one of these would be considered the control group? The one that you're not doing anything different to, it's where you're collecting your baseline data, and that would be the group that gets no water. Because you're trying to pick out what type of water is going to affect plant growth. What are you going to keep constant? What are you not going to change? Because you're not testing these things, but you need to keep the same for all of them so you can get reliable data. We'd want to keep the amount of water the same in all of them. Write that down. Amount of water. The type of plant would be the same. Soil. The type of soil, the amount of soil. Sunlight, you'd want to make sure they get the same amount of sunlight. The temperature. Put temp. So those things are some of the examples of constants that you're not testing those things, but you want it to be the exact same for all of them. The independent variable is what you're testing, and you're testing the type of water. So I'm just going to shorten it to 2 words and put water type. You could put type of water, that's fine. The dependent variable is what you're measuring, and you're measuring plant growth. So independent variable, dependent variable. So plant growth, let's write that in down below. Plant growth. We'll do one more example. Which substance will melt ice the fastest? Our control group is what we're not doing any testing to. We're just going to make the normal one. So that's actually called the normal one. The normal, which is right here. Just ice being normal. Constants. What are we going to keep constants here? What are we not testing, but we have to keep the same for each one is, I would say, the amount of ice. And the amount of the substance. The independent variable, we go back to our sentence, our well-defined question here, and pick out the independent variable, which is the cause or what we are testing. What are we testing? Which substance will melt ice faster? So we're testing different substances. As you can see, they're testing salt, baking soda, cold water, hot water, sugar, to see which one's going to melt ice. And then our dependent variable is what we're measuring is how long it takes the ice to melt. How long for ice to melt. Okay. Lastly, on here, well, I shouldn't say last, second to last is when you have a science report, you actually are going to work on something called claim, evidence, and justification. And I want to give you just a brief description about what each part is. So let's write them in. A claim is a statement that answers the question. The question is your well-defined question that you're testing. It's a statement that answers the question. Also, there's a chart here, if you just keep scrolling, and it gives you a little bit more about how you write a claim. I really like this chart here, so it definitely is a good point of reference when you are writing your own claim. As it says, it's a one sentence answer to the question you investigated. It answers, what can you conclude? It should not start with yes or no, and it should describe the relationship between the dependent and independent variables. Then you will be providing evidence, because after you test, you're going to collect data and use it in your evidence. The evidence is the scientific data and details that support your claim. It will include qualitative, there's that word again, Qualitative, qualitative and quantitative data. Quantitative, Quantitative, and then I'm going to add the word data. So it's going to include your qualitative and quantitative data and all your evidence you've collected from your experiment. So what the chart says about evidence is must be sufficient. You need enough evidence to support your claim. Appropriate, use data that supports your claim. Leave out information that doesn't support your claim. It should use one or both types of key observations, which we talked about. Then you have your justification, where you tie it all together and you're justifying why your claim is correct. It explains the how or why the evidence supports the claim. Use your research and scientific principles to help you support your claim. Scientific principles are things that you learn in science, like, what density is, or what different types of measurements do. Just different things that you learn in science, different topics that you learn in science. Justification, down here on our chart, ties together the claim and the evidence. It shows how or why the data count as evidence to support the claim, as I stated, provides a justification for why this evidence is important to this claim. It includes one or more scientific principles that are important to the claim and evidence. It's a very thorough scientific explanation. Lastly, let's see a typo here. There you go. I don't know if that's right, the word annotate, but you're going to read, highlight, annotate below. You have a whole section about graphing and about the 3 types of graphs right here. Line graph, when you use a line graph, bar graph, pie chart. Right here it talks about the X and Y axis, a data table when we use that, and then something called the Sultan method. Sultan stands for scale, units, labels, title, accuracy, and neatness. These are the different things you must include in a graph, so you do need to read over this and annotate it, highlight, just to make sure you're ready with remind yourself of all the graphing rules. Make sure you have a completed copy of these notes in your ISN and use them as a reference when needed. All right. Thanks for listening.